And I will have it running on the side, but I'm going to mute it, of course, because otherwise it will be a problem again.
Yeah.
But I think we are set. All right, let's see. Okay. Hello, everyone. So today we are here at another talk of ours from SJAA. We are an astronomy club here in San Jose, California, for those who are joining us from places afar. And like our speaker actually is in Seattle right now. So this is a COVID adaptation of our speaker program. And I'm very happy that it has allowed us to reach out to people outside San Jose or outside Bay Area, California, and actually also have speakers join us from other parts of the world and the country at a minimum. So to give you a brief background on the club, we have been around for, I actually don't know the exact number of years, but like it's close to 25 years or plus more than that. And we are a very active club. We have like about 350 to 400 members, and all of us are just basically really enthusiastic about astronomy and like what we like to learn on our own. All of us are also very learning on our own, kind of like amateur astronomers is the typical term used, where we just study astronomy on our own, just play with the telescopes and like do the stargazing whenever the time allows us to do so. So today we have one of our programs that we do, which is speaker program. And today we have somebody join us from Seattle, like I mentioned. His name is Tom Field. He is the contributing editor of Sky and Telescope magazine, which is pretty cool. And I was just chatting with Tom before this talk began, and we were just wondering, like, how is it possible that we have not had him before to come and give a talk for us? So I'm really glad that he actually reached out, and we could schedule this talk with you today, because he's also an author of RSpec software, which is what he's going to talk to us about today, as you can see. And I guess I will hand it over to Tom now and have you start, Tom. Thank you.
Thank you, Sukada, and thank you also for doing all the background work to get this arranged. I think some people sometimes don't realize how much work it is to get all the schedules right and URLs and all that. So thank you for that, and thanks to the club for inviting me. I appreciate the opportunity to speak to you. I'm going to talk for 45 or 50 minutes, and again, because we're doing this on YouTube, it's not quite bi-directional. You get to see me, but I don't get to see you. So, and then afterwards we'll do Q&A. You know, I understand that as I had some communications with the imaging group at one point there, and we were talking about my speaking, and I'm happy to speak to them on a different occasion or answer questions or whatever. I love the field, and I think you'll hear that as we go through the presentation tonight. So how have we managed to discover so much about the universe when really we haven't even left home? You know, we're still in our very localized region. Of course, images, we can see the universe in 2 dimensions, and with eclipses, we can see a little bit of, you know, 3D or depth, z-axis. And then if you wait a while, the time dimension reveals you can see some of the stars. There's one in the upper right-hand corner for a moment or for a second, you can see changing. These standard candles, these are Lyrae stars. If we spread the colors out, we get an as-if 5th dimension. Notice the air quotes. This is the spectrum of the sun, as it turns out, and all those dark lines actually have meaning. It's beautiful aesthetically too. I love to look at the colors and go, well, where does this blue turn to green, you know, or where does this, you know, green, or, you know, all those transitions, very smooth. These barcodes help us understand a lot about the stars. They say 70 or 80% of the research that's done in astronomy is done using spectroscopy. In my next life, I'm going to choose a field where there are fewer syllables in the specialty that I'm involved in. Spectroscopy can be a mouthful. But these barcodes can show us a lot of different things. I won't read the bullets here because I'm going to give you some examples of these as we go through tonight. So let's just get started by talking a little bit about the science, just to get everybody to the same level. Forgive me if you're familiar with this. I'll try and move quickly through this. The good news is you don't have to know a lot of science. Thank goodness you don't have to have a PhD to do spectroscopy. I don't have an undergraduate degree in science. And in fact, I had a quote that I put up on a talk I gave earlier today. I haven't decided whether to incorporate it into my general talks. And that is, the quote went something like, if you were going to wait till you had a PhD in astrophysics to do astronomy, ... you wouldn't be an amateur astronomer today. So don't let your lack of knowledge keep you from starting something like this. There are some things that are quite difficult to do, but this is not one of them. So Sir Isaac Newton, of course, discovered that we could pass light through a prism and split it into its component colors. We can also bounce it off of a DVD, a finely lined surface like a DVD, or even pass it through a ruled piece of glass called a diffraction grating. Bunsen, he was the first person to actually systematically study spectra. He burnt samples in a flame and he put the light through a prism and he looked at the results. He was a pyromaniac. He burned everything he could find. And the great thing is that he kept notes really clearly. So he created a catalog that has served us, its great-great-great-great-great-grandchild has served us today, as we'll see in a few minutes. Over on the right here, this guy Kirchhoff was a contemporary, a colleague of his. We won't spend a lot of time with him, but the one thing I wanted to point out related to what he thought about, and that was that some spectra have like a rainbow in the background with gaps. You can see those gaps there. And other spectra have a more or less black background and lines. Now, the nice thing about this is, regardless of which it is, the lines or the gaps are in the same position. Now, which one you get depends on things we won't talk about, that Kirchhoff talked about, the temperature of the gas that the light is going through, things like that. But because we'll see examples of these too, I just wanted to point this out as we get started. You can see these lines here are unique for each element. So for example, this line here in hydrogen, if we burn hydrogen and look at it through a prism or a diffraction grating, that line doesn't appear if we were to burn helium. So, and in fact, hydrogen is, of course, is so common in the universe and we use it so often that it's nice to have this term for all of the lines in hydrogen called the hydrogen bomber lines. And we've even named the lines with Greek letters, like we name the stars in constellations by intensity by other Greek letters. So for example, hydrogen beta here, that's sort of that's like robin egg blue, for example. And there's the gamma and the alpha and the red. Here's a periodic table I created a few years ago. We sell most of them to schools, chemistry, physics, astronomy departments, and some amateurs get them too, the real nerds. So I've got one. And in fact, I can brag, Neil deGrasse Tyson told me he has one hanging on the wall of his office. So we're happy about that. Also, there's one on the Sophia Boeing 747 airborne telescope. So if we look over here at hydrogen, you can see there's the hydrogen bomber series, the hydrogen alpha, there's that beta, that robin egg blue. But if we look, for example, at helium, like the helium that you might put in a balloon that you bought at the florist where they filled it for you, very different lines. So these really are fingerprints. So these days we don't have to actually burn things. We have gas tubes. And let's see if I can show you one here. Here's a gas tube over here. I can turn it on. You can see the brightness there. It's just a tube with some sort of rarefied gas in it. In this case, maybe you can see the lettering there. It's helium. So, and this is actually a device that we use in our in classrooms. This is a little spectrometer that works with our software that physics and chemistry and, as I mentioned, astronomy teachers use to teach those topics. And we have a lot of those around the world in a lot of different schools. The closest one to you, I can't remember the name of it. I'll think of it while we're talking tonight. So far, everybody I've mentioned have been old white men. What about some people who aren't old white men? We saw a great example of a non-old white man, a man giving a speech earlier today, some of you may have. But let's look at Annie Jump Cannon and her women, called the computers. They were prohibited because of their gender about 100 years ago from accessing the telescopes at Harvard. So what they did is they studied these glass film plates of spectra, and they studied hundreds of thousands of plates, and they were really good at it. And they, as a result of their exposure to so much data and their insight and creativity, they created a star classification system that has helped us understand the evolution of stars. Another example is Priyamvata Nataraja. She's at Yale, and she studies hyperactive black holes. Nancy Grace Roman was the first astronomer at NASA. She got her PhD in the 1940s. She was a big proponent of the Hubble Space Telescope, which is in the background there. Thankfully, she had a hand in making it happen. Elisa Quintana studies exoplanets and has discovered some in the Goldilocks zone around some red giants where there might be water and thus perhaps life of the sort we're familiar with. And finally, Jedediah Eisler she's at Dartmouth, and she studies gravitational lensing around black holes. So this is a new slide for my presentation that I made this summer. It was really fun putting together because there were just so many amazing women in the field. And again, we've made some progress. We've got a lot further to go in terms of equality. So what I want to talk about tonight is this grading here. It's a star analyzer grading. It costs about $200, and that's all you need to add to your current kit to do this. So if people are thinking or telling you, oh man, you're going to have to spend thousands of dollars and really carefully calibrate all these things that you've never used before, couple $100 gets you started really simply. So here's some examples of how we might mount a star analyzer grading. In the upper left there, you can see in my video here, here's a DSLR with, this is just a little adapter that we offer. It screws into the lens cap threads like that, and then you can put the grading in. Now it's, of course, this is relatively low resolution and a very small aperture, but you can actually do DSLR spectroscopy. With the grading here before the lens, it's called an objective grading. And some people, even though they have much more sophisticated gear, also use this to capture interesting spectra. I'll show you, for example, one of a comet in a few minutes. Here's just an example of a FITS camera. It could be cooled, uncooled. On the lower right there, again, that's like one of these ZWO cameras where, again, fortunately, the grading often just screws directly into the nose piece. I need one more hand here in order to accomplish that. And we'll talk about mounting in a little bit also. Can be color, can be mono, as I mentioned, or you can put it in a filter wheel. So there's lots of ways to use these gratings. Now, the other thing to mention about DSLRs is that you can piggyback on your current equipment, so you're not messing around with whatever imaging equipment you have set up at the prime focus. Okay, so enough history, theory, equipment. What can we actually do? We're doers, and I know that the club has a lot of imagers, as I've heard. So fortunately, I know you'll be interested to hear what's accomplishable. What a word, what adjective. So we take the starlight and we put it through a grating. We get that rainbow spectrum, and the starlight also, some of it goes straight through, and we can capture that on our sensor. Let's look at our first example. It's really an amazing one. So these are all different spectra captured at a different time by Torsten Hansen. And look, he used just an 8-inch Newtonian with an imaging source video camera. So, and these stars are in temperature order. So at the top, we have these B stars. And then as we go down here, they get cooler and cooler down to the type M stars, the cool stars. So they're in Ophiophainge KM order. And I forgot I wanted to bring it up. I've been looking for a better mnemonic for that. So I've got it. I found one on my phone the other day while I was waiting for something. It's not great, but I wanted one that wasn't gender specific. And this says, and this may apply to the club. I know a lot of clubs have a lot of people to whom this would apply. Okay, boomer, a fully green kilowatt matters. Ophiophainge KM. So I don't want to get into a lot of detail on this screen except to show you two things. Notice how different the spectra are by temperature. So this is how astronomers actually tell the different temperatures of stars. And if we look down here at this region, I mean, that's not like a line, that's like a forest of lines, right? Well, on these cooler type M stars, they're cool enough that in the outer atmosphere, in the outer shell, some more complex molecules than just hydrogen or helium, these are actually titanium oxide, can survive without getting incinerated. Now, truth be told, I don't know anything else more about titanium oxide than what I've just told you. The great thing about being the adults we are and spectroscopy is you don't have to dig down deep, deep, deep and study for the final exam. You learn as much as you want, and there's lots of different places to learn things. The other thing I wanted to show you here, if I can find my mouse, is these lines here. So these lines, which come all the way down here to about 4,800, notice they're different prominence. And this one is the most prominent on this type A star, like Vega, for example. So here's the deal. The way these lines get made, you may remember some of this from school, is in the Bohr model of the atom, we have these orbits that the electrons are in, and sometimes they jump either up or down between orbits. And this is what in the robin egg blue. So that's the hydrogen beta, and that's the jump from orbit 4 to orbit 2. It's again when it's jumping up. So there's this jumping up and down, and you get either emission lines or absorption lines depending on the jumping. We need not get into that detail. So on these hotter stars, a lot of the electrons, they get pumped up, but they go, because the stars are more energetic because they're hot, right past level 4 and out perhaps. So we don't have as many electrons sitting at 4 to drop down between 2 and 4. And the same thing down here, these stars, these F and K and M stars are so cool that a lot of the electrons never get pumped up that high. So they're like hanging out in here, so we don't have as strong a line. So this is the kind of thing that we can do, and to do it with a video camera. In fact, this is something I wanted to mention is spectroscopy is really a lot more immune to urban light pollution, because unlike the video imaging that you do, and I know you all, some of you go out to Morgan Hill and other dark sky, relatively dark sky sites, because you are imagers, you know how problematic urban light pollution is. Everybody pretty much knows. But with imaging, we're really interested in the aesthetic quality and the balance, and we do a lot of tweaking, and we need all the photons we can get with the best signal noise, let's say. So, but with spectroscopy, because we're doing science, we don't want to mess with the photons after they've hit our sensor. We don't want to be tweaking or enhancing in any way. And as I said, because we're just looking for peaks and valleys rather than the overall aesthetic balance and contrast and so forth, we can do a lot more in the city, which means that a lot of people do this in the city, and then when they go out to the country, or the dark sky sites, they do a little bit more deep imaging, or if they get really hooked on spectroscopy, they just do more spectroscopy out there with dark skies. So you see that crosshairs there? Well, maybe you can see in there that there's a little bit of dimming in that robin egg blue. But if I had time on, let's say, the Hubble Space Telescope, and I was capturing spectra, and I wrote a paper that said, yeah, we captured the spectrum, and we got a little dimming in the robin egg blue. That's not publishable, is it? So we have to become quantitative. And to do that, we graph the intensity of this region. It's really pretty straightforward. This axis here is intensity. And you can see the star, for example, is very bright and narrow. So this is a very high peak, and it's not very wide. Whereas this thing is very wide, and it's sort of dim in this area, and then it gets brighter, 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 and then dimmer, dimmer, dimmer. So this starts at dim and gets brighter, 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 and dimmer, dimmer, dimmer. But look at this. See that dip? That's where the science is. Now, even though we can't quite see it visually, and there's another dip there maybe that's down there, and that dip might be that. In order to do science, now we can measure the full width half maximum of that dip. We can look at the area that's enclosed by that dip, or look at how it relates to other stars, or this star on other nights, or other pieces of equipment. So Now we can compare our work to others. So how do we get those graphs? Well, my story is I've been an amateur since about 1990. But in about 2009, I wanted to do some science. And so I got a grating. Went out in my backyard. I've got a SCT, an 8-inch, just like you said you have, Sukada, in fact. I went out in the yard. It's right outside the window there, if I can get my pointer finger in the view. And it was a Saturday night. I'm 3 miles from Pike Place Market. I'm more or less in downtown. And I came in at midnight, and I found it the other day. I was cleaning my office. I was just using this Logitech webcam. You can still see the residue of the duct tape as I duct taped it to the nose piece or a barrel on an eyepiece. And I mean, it was a mess. I came in at midnight. I had some video of Vega. I had a sore neck. My knees on my blue jeans were grass stained. Well, it's Vega in August. What do you expect? And Sunday morning, and this literally is that image. Sunday morning, I wanted to create this graph, and I failed. I downloaded the freeware that was out there. I had trouble installing it. It was like DLL hell. It was crashing. Half of it was in French, and there was no manual. And it just wasn't up to the usability level that we're all accustomed to these days. And so I quit. I gave up. I'm a little embarrassed to admit that. Who likes to admit they've quit? I told my wife, I said, look, I'm supposed to be having fun. This is a hobby. This isn't a job. I had fun in my job too, but I couldn't just quit as easily as I could quit this. So I put the grating in the drawer. Well, a few weeks went by and it kept bugging me because I really wanted to do this. And so I figured, okay, Saturday at the end of the work week, I wished it was always the end of the work week, but work these days is often 7 days a week. So I figured I'd just write a piece of software to generate this curve. And I did. Sunday morning, I was done. And now, I don't know, 10 or 15,000 hours later, the software is almost done. My wife keeps saying, would you finish the software so we can start having dinner together on time? It's done. But, the thing is that I didn't intend to create a product. I had my other job and everything, but people really got excited about what I'd done. One of the obstacles to starting something new like spectroscopy is, oh no, another piece of software to learn, another learning curve. So I want to relieve you of that misconception. Now, I know it's after dinner here. I talk to a lot of clubs back east, and it'll be 4 o'clock here and 7 o'clock there. And it's always after dinner for them. But for all of us here on the West Coast, now it's nice to talk to a club on the West Coast for me. I know it's after dinner. I'll lose you if this turns into a software demonstration. I know I will. So I don't want to spend much time with this, but I do want to show you a screen or two because I think it's important for you to see how easy it is to do. So here's an image. It happens to be in color. Of course, color cameras aren't quite as sensitive, and they have some other scientific shortcomings. Color's great, though, for outreach and also for people, newcomers, to sort of understand what's going on. There's the star, there's the spectrum, there's a gap, there's maybe some gaps there. All we do is bracket in our spectrum like that, and we have that intensity curve over here. That peak is the star, and this thing here is that. And see that gap right there? It's that dip. That's oxygen in the atmosphere. So, and that dip there in the robin egg blue, what do you suppose that is? That's our hydrogen beta line. So how do we identify all these dips? Well, remember I mentioned that Bunsen created a catalog, and the grand catalog descendant is one that still serves us all today. And it's built into the software here. I can come down and say, just 2 or 3 more clicks and we're done with the software. But I can come down here and say, show me where the Balmer series would be. If there are dips where all these lines are, we can be pretty sure somewhere between us and the star, there's some hydrogen that's absorbing some light because of those electrons jumping. And look, we've got a dip there, one matches there. Isn't that amazing? So now with a backyard telescope, this is literally a frame from that first video I shot. Backyard telescope in the city, we're detecting scientific data from a distant star. I'll show you some distant objects that are billions of light years away in a few minutes. So this is actually a frame from the video I first shot that night. I'm going to play it back here at 2 frames per second. Now the image here is jumping around because my seeing, so is the graph, okay? Now, we're all familiar with stacking, how we can average out noise. This is fun to watch. I'll watch this. This will be the last thing I show you here. There's our hydrogen alpha line there. We can see the little label, but notice that dip is sort of coming and going and moving around because of our noise. Let's turn on simple stacking in the software. Watch how in a matter of a few seconds, maybe 10 or 15 frames, that dip becomes very stable. The video is still playing, but now we've averaged out all that noise. So that's really all I wanted to show you here. The only other thing I'd ask you is to remember, let's get the right key here. In your mind's eye, if you would remember that view, happens to be Vega. It's a type A star, but we've got these lines showing the Bomber series because I'm going to show you some discoveries that were made with this data as we go forward tonight. So let me get the right screen up here. There we go. Get rid of that thing. There. So here's a cool thing. Oh, in fact, now that I left that screen, I meant to mention to you just one more thing here. I won't click anything. This is a fantastic screen for when you're doing outreach because the color and the movement, and even better yet, it can act as a platform for you to transition into a scientific discussion. You don't have to know a lot, but to talk with people a little bit about how we understand the stars can go a long way. Now, the other thing you can do is you can go and look how sometimes those dips are really deep, just depending on our seeing. You can also go into a high school or even a middle school and volunteer your time. It's one thing to go in and go, hey, we're going to look at the sun or something. It's another thing to say, we've got some science to do here. And you can act as a mentor to high school students, and it's incredibly rewarding. So let me stop that playback and now head back to the software. This is an example of some outreach that you could do. This is of a gas tube. It's my software. This is actually in Marseille, France. This might not be something you do at a dark sky site with all that light, but they transitioned into looking at stars after this introduction. So here's a DSLR image with the grating on the nose piece, and you can see some stars and their associated spectra. There's a gap there. Here's a star here with these lumps, right? Well, those are emission lines. They were so bright, they saturated our pixels. We got some blooming. But let's look at a Wolf-Rayet star here. Now, I have a confession to make to the group. When Janet Simpson, I couldn't remember her name. I've probably said it 400 times. When Janet Simpson sent me this some years ago, I couldn't remember what a Wolf-Rayet star was. Now, maybe you're in the same shoes, which is pretty much why I'm telling you this. I'd read about Wolf-Rayet stars a handful of times or more over the 20 or 30 years before I got this. But things do go in one ear and out the other. What I found, and the reason I bring this up is what I found is, and you may have found this if you're an imager. And by the way, if you're not an imager, I should have said this earlier before you tuned out. If you're not an imager, even following along tonight, I think that you'll learn a lot about how imaging and how spectra get captured, and that will serve you while you're reading magazines or things online. So this isn't just a talk for imagers who might want to do this kind of thing. So Wikipedia is our friend, right? Wolf-Rayet stars are late stage stars headed perhaps to becoming a supernova. They're massive. They're 25 times as large as the sun. Very hot, intense stellar winds dissipating the outer shell. And here's what that emission spectra, right? These peaks look like: carbon, carbon, carbon. Why would we be seeing carbon? Well, remember, stars burn through the elements one by one, hydrogen, helium, on up. And part of that process, as the star has matured, has involved carbon. And we're seeing that glowing carbon, or you could almost call it soot. It's not really soot, but this is the kind of thing. And look at the numbers at the bottom there, 30 seconds with a DSLR. Who would have thought? So this is an emission object. And the reason, by the way, we can see these peaks with such simple gear is because that intense stellar wind has widened those peaks from what they would normally be. Let's look at another emission object, our beloved ring nebula. There's what it looks like. You can see there's just two colors or two elements emitting here. We have hydrogen alpha and we have an ionized oxygen. That's what that Roman numeral 3 means. If you're not familiar with that, it just means some of the electrons have been pulled out. So But most extended objects, other than this one, are pretty boring without a slit, if it's just this. And so, in fact, let me show you an extended object with a slit spectrometer. First of all, here are the slit devices that typically amateurs use. You can see they're like an order of magnitude more expensive and probably equally that much harder to use, because now you're acquiring your target and guiding on it, having to track it on like a 20 micron slit. So almost nobody, I mean, literally 1 in 100 people start with these. Almost everybody starts with this to understand the field and to get that foundation of skills as well as knowledge. But here's a slit spectrometer image of Orion Nebula. Here are these emission peaks, and there's our red hydrogen alpha, and there's that ionized oxygen with that Roman numeral 3. Of course, this is the beginning of stars rather than the end of stars like that Wolf-Rayet star. So now, real quickly, since we're not in Zoom, I can't query you live. And I know it's the topic of religious wars as to whether to use Zoom or not. I prefer Zoom, although the club has good reason to use YouTube for presentations like this, because that way we can break out and have discussions. But so my story, instead of querying you on yours, and yours probably is not all that different than this, I wanted to do astronomy. I found a club. I was living in Denver. I went out one night in the city, first quarter star party. I walked out on the observing field. I'd never seen telescopes before, but I'd seen pictures in magazines. And I look out on the observing field. You know, it's sort of cool when you can remember when you didn't know something. When I looked at that observing field, honest truth here, I looked and went, what are all, you know, those cannons that they shoot people out of in the circus? That's what I thought I'm going, what is this? What? I thought I was going to see telescopes. Of course they were Dobbs, but I didn't know any better. I queued up at a Dobbs. Somebody was running it, much like some of you and I have done. They were pointing at M42. I was all excited. And, you know, I got up to the front of the line. I looked through the telescope and I was really let down. I was really disappointed. It was a smudge. That's the most common word I hear when I ask club meetings to describe their first experience with M42. It's a smudge. It was mono. It was nothing. So fortunately, I kept with it, as did all of you, or you wouldn't be here today. So why do I still go back as well as you go back to look at M42? What's changed? Well, again, we've got better telescopes, you know, we're at better observing sites. And also we've gotten much better at averted vision, right? So you can actually look at stars through averted vision and you know, use the more sensitive part of your eyes. But seriously, I think the reason we go back is because now when we go back, we understand what it is we're looking at. We know it's the stellar nursery, the birthplace of stars. And the reason I mention this is because when we bring that understanding to our visual observing, it gets that much more interesting. It's a much deeper experience. And that's something that spectroscopy has done for me. Again, I'm going to sound like I know what I'm talking about tonight, but don't let me fool you. Really, I'm a knuckle-dragging programmer with apologies to the Silicon Valley crowd I'm talking to. So you don't have to know a lot. And as you learn spectroscopy, your knowledge will increase. So here's an example of Uranus and Neptune. You can see in the spectra themselves these big gaps. And of course, there it is on the intensity graph. And there is that band. What did we learn earlier about type M stars when we saw a band? That meant that it was relatively cool and some more complex molecules could exist. Well, these, of course, aren't stars, but they are cool. And what we're seeing here is a complex molecule with, again, same guy, Torsten Hansen, using that 8-inch Newtonian and a camera like this. It's the imaging source, but in this case, most of us would use perhaps a ZWO camera or a Malin cam. So with quarter-second exposures, you know, running at 4 frames a second or even slower, we're able to capture the methane on these planets, the atmosphere. And of course, one of the ways that we are searching, and we'll eventually, if we do detect ET, some sort of extraterrestrial life, will be by observing the atmosphere of these exoplanets, much like we observed something in Venus not long ago. We're not sure what it showed us at this point, but it's cool that we can do that ourselves. So in 1881, Henry Draper, that's the Draper catalog guy. He observed the spectrum of a comet. You know, I just leaned on my monitor here and I'm wondering whether things are bouncing around a little bit. I've got 3 monitors spread out here, so I'll try and avoid doing that.
Don't worry, Tom. It looks great.
Okay, good, thanks.
Yeah.
So there's a spectrum of a comet. It's pretty in itself. And there you can see the intensity peaks, the swan bands, those are carbon. Now, this is, you know, pretty cool. It's an extended object, but it's compact enough that we can still use a slitless, inexpensive grating like this. So this was captured by Vikram Agnihotri. He's a nuclear power plant engineer in Rajasthan in northwest India. And in 2013, I'm dating myself, in 2013, he was a newcomer. And now today he's a real expert and I learned from him. What teacher doesn't want to learn from their student? Really, it's just wonderful to talk with him. And again, I spend a lot of time mentoring and teaching amateurs and even high school students because it's just fun. It's something that I enjoy doing, very nourishing for me. So here's another more timely example. We can see the peak here in the yellow for the sodium in NEO-WISE. And this is, you see that word objective grating. I'm not sure I mentioned that to you, but that's when we have the grating on the front of a DSLR. In this case, the comet was pretty bright, so we didn't need a lot of aperture. And that's how this guy chose to do it. He's a German man. Now, anybody who uses a C-clamp, that's my kind of amateur. I break just about everything. You know, in fact, that's another reason I like the grating is because it's tough to break. Now that I've lost it, oh, here it is. So, but this was a spectrum and a setup put together by a guy named Robin Leadbeater, who designed the star analyzer, actually. See, my problem is since I break everything, in fact, you know, my favorite command in Windows is Control-Z or Edit Undo. But I'd probably have cranked that C-clamp down too tight and collapsed the camera housing and destroyed the camera. So he didn't, thank goodness. He attached a star analyzer to the video camera in a Perseid meteor shower. And here's excuse me, a single frame that he captured. So in the time of that one frame, the meteor moved that far. And this is the spectrum over here. And that gap that's right there is that dip in intensity. So let me drink something here. Excuse me. So this is rather specialized, right? There aren't meteors every night to look at and you've got to capture them right. And, you know, there's lots of challenges, but some people love doing this thing, whatever floats your boat, why not? So we're not going to spend much time talking about the flash spectrum, but again, one advantage of low resolution spectroscopy like this is you can get the whole spectrum in one view. And we've heard a lot about the sun recently. We will be again in the next several years. Just to point out here that it was in 1868, we observed during a total eclipse of the sun, this yellow line. We didn't know what it was. Bunsen hadn't cataloged anything with that yellow line. So they just figured, okay, we don't know what it is. It's on the sun. Greek for sun is Helios. Let's give it the name Helium. Now you fast forward 20 or 30 or 40 years, a couple of researchers discovered spectroscopically a gas here on Earth that they had created that had the same yellow line. They had discovered helium here on the Earth after we had already identified a physical property of it on the sun. It's an amazing story and told rather quickly. Sorry for the speed. Do you feel like you're drinking from a fire hose? I apologize. So novae with a DSLR, you can see some have iron absorption lines, others don't, if that's something that you're interested in doing. A quick reminder about Doppler Shift. Again, it's the change in pitch or wavelength of sound that's moving towards or away from us. A common example is when a train goes through the station, it goes, air, right? So higher coming towards you, lower going away. Well, the same thing happens to light. So if we were expecting to see this triplet, I love the term, it's almost self-defining, right there, and instead we saw it shoved over to the right, what would that mean? Well, that would mean that it was moving away from us, right? As the car moves away from us, the sound is stretched a little longer, lower. That would be redshift. But on the other hand, if it was over here instead of where we expected it, we'd know that the object was moving towards us, or blue shift. Let's look at a really cool example. So supernovas, there's a lot of different exploding stars. Again, some of you, probably more than a handful, know more about this topic than I do. But there's different types of supernovae. One particular type is called a type 1A. And it's basically a binary system. You know, I've shown this slide and spoken about it a lot. And just this morning, literally, I looked at this term and went binary pair. Does that mean four? How do you do that? 4 stars? You know, it's a binary system. It's 2 stars. So without getting into the details, enough of our wordplay. A type 1A supernova is when a really hot star dumps gas onto a white dwarf. And when you put gas onto a hot surface, what happens? It explodes. So here's a supernova in M101. There it is, for a brief time brighter than all of the stars in its galaxy. Now, this is a type 1A supernova. There's a photograph of another type 1A, not this one, but you can see there's that sort of, it looks somewhat like a sphere, you know, like it's a little more transparent edge on here than on the edges and on the limb, shall we say. So what about this supernova? Well, there's its spectrum captured with our star analyzer grating by David Strange with a 9-inch SCT and less than 15 minutes worth of stacked images. And there's the profile intensity graph. Now you can see a little dimming here, but look how bright it is in the graph. Now, you know, it's almost an overused phrase. I sometimes wonder whether I should just dump it. But, you know, they say we're standing on the shoulders of the giants. And the giants are really smart men and women. And they figured out that the different types of supernova, just like the elements, the different types of supernova, whether it's this binary system or whether it's a single star collapsing on itself, a core collapse when it runs out of fuel, they all have different fingerprint spectra. Now, this next slide, it's not going to be on the quiz, but here it is. For a type 1A supernova, notice that deep dip right there around 6,000. That's silicon. But these other core collapse spectra, these down here, they don't have a deep dip in silicon. They have other fingerprints, like this type 2 has a very strong emission line. That's a hydrogen emission line. But we can use these fingerprints as amateurs to determine and identify supernova types. This is one way that amateurs can contribute to the professional community. Tim Puckett, for example, a few years ago showed a slide at a conference I was at with, it was an Excel worksheet with all these supernovae that had never really had confirming data on them. Now, the problem is supernovae are often somewhat dim, so it's not quite as easy or frequent a circumstance that you could do all the time. But let me show you one of the cool things that David Strange and I did. First of all, we noted the wavelength of that dip at 6150. So we made note of that. Then we looked up online what the wavelength of silicon would be if, for example, Bunsen had burnt beach sand. That's good. Bunsen burnt beach sand. That's hard to say. So that's the stationary wavelength of silicon being burnt. Now, the difference between those is Doppler shift. Something's moving. I couldn't remember the Doppler shift formula, but Wikipedia is your friend, and you plug the numbers in, and now we have measured the blue shift of the shell of that supernova as it races towards us. This shell is expanding at 22 million miles per hour, and we've just measured it on a backyard telescope. Now, you may remember this guy, Adam Rees, when he won his Nobel Prize, it was for work that he and his team did just before the turn of the century, studying the accelerating cosmological expansion. And what did he use for standard candles? Type 1A supernovae. And now we've measured the expansion rate, not necessarily the radial velocity, but the expansion rate, which would have given us a distance, the expansion rate of that shell. Now, in bang for your buck, we do pretty well with this compared to his multi-million-dollar telescopes. But it's sort of fun to be able to duplicate some of the science that's been done. What about the spectrum of a black hole? Well, of course, black holes don't emit light, but the accretion disk, as matter spirals in, gets very hot as it moves quickly. David Hayworth down in Portland, Oregon, captured 3C273. I've never imaged it. There's its spectrum. The spectrum's there and those two little dots at the arrowheads. Let's zoom in on it. There they are. There's the profile intensity graph. Now, this guy, one of the reasons I love to be able to see a group in a Zoom meeting is that if there's any people who are younger there, I can point them out. Because this guy was only 25 in the 1960s when he studied this. And he was really frustrated. The reason I know this is there's this wonderful transcript where he describes this discovery, as well as his fears and the challenges. And it's linked to on our site, and I can get you the link if you can't find it. Just contact me via our contact form. So he couldn't figure out what these peaks were. So he said, in much of the science we do, we eliminate things as to being, well, that's not that. We see what's left. So he said, well, let's just eliminate those from being the hydrogen bomber lines. So he brought up the reference lines for hydrogen bomber. And this is that image from my software I asked you to keep in your mind's eye. Not for the Vega part, but this is a hydrogen alpha, beta, right, in that robin egg blue, gamma, and so forth. But those lines don't line up at all with this data, right? There's no big peak right here. There's no peaks out here that are big. So Martin Schmidt was able to conclude, well, whatever these emission lines are on this object, it's not hydrogen anyway, except it was massively shifted to the right, red shifted. And he figured that out. When he went, he was really scared. You know, he conferred with his colleagues before publishing. You know, he was afraid he was making a simple, stupid mistake, and people were going to point out how big and careless he was to make that mistake. When he went home that night, he says he told his wife, something really terrible happened in the lab today. The reason he said that is he realized that if he was right, there was going to be a lot of celebritydom and just, you know, waste of his time in his mind. So if you use the Hubble constant, you can calculate that this object from that redshift, again, it's not hard math, it's just like the math we saw a moment ago, is 2.5 billion light years away, approximately. What amazes me is that light can come from such a great distance over such a great period of time, and still we can tease out some information about that object. The discovery here was that this object was so far away and yet so bright to our eyes and our instruments that it had to be enormously intrinsically bright. And I think I lost it. I had something which described how bright it is intrinsically. We'll see if it comes up on the next slide. So not everything ages as well as light. Here's Martin Schmidt, you know, a couple years ago. And people, believe me, I've been justly accused of throwing rocks in a glass house when I put these two images up. Listen, he has a full head of hair. You know, I'm envious of the guy. Give me that anyway. So now suppose we wanted to look at the details of this hydrogen alpha feature. So I wish it was as simple as just rolling our mouse wheel, right, and zooming in. But at some point that becomes like adding empty magnification on your telescope to look at the moon. It doesn't get any more crisp or clear. It just gets bigger. It's empty magnification. So to look at the details, then we do need to use one of those slit spectrometers. And I wanted to show you some examples of the higher end work that we or professionals can do. So the first thing, there is an amplified or higher resolution hydrogen alpha dip from Vega. Very sharp dip. Look at all those features. Those are probably all things that could be identified. So as I said, often in science, we just compare two things to see how they differ. So I'm going to put up on the right the spectrum of the moon, which isn't really moving towards or away from us appreciably. There's the moon. Look how they're not in the same place. That difference is again from Doppler shift between the moon in blue and Vega in fuchsia, right? So, and we can use that difference to measure the radial velocity of Vega. And we calculated it here at 20 kilometers per second, and the published value is 14, pretty amazing. So in fact, this might be a good point just to take a brief moment. We got one more example and then we'll finish up. My wife always says to dress for success, you know? And this is the hydrogen beta in red through here. And I know it's a mess, I apologize. You know, the thing is, I mean, and some of you at home are going to know exactly what I'm talking about here. You and your spouse have encountered this perhaps. I'm having trouble finding a salon that's open and has time for me. I call around, they're just not, like I said, it's a common problem these days. I'm hoping that it's, like I said, it's a mess. Now, my wife does tell me dress for success, but she assures me this is not it. I love it. It also keeps me warm on those cold nights. So here's our final example. I need this visual aid. It's a star that's spinning very fast. And here we have this edge of the star is coming towards you. So that light is a little bit red shifted, blue shifted. And this light is moving away from you. So it's a little bit red shifted. So let's see what that looks like. Well, here's Vega, which isn't spinning very quickly. But if the star, this is just another explanation, the star is spinning like this, the light coming off this edge is coming towards you. So it's blue shifted and this light is red shifted. So what we'd expect is that some of the light that would normally be here is going to be here red shifted and here blue shifted. Let's see what that looks like. There's Altair in blue. Look how broadened, I was going to say smashed, but that didn't sound like the scientific term. So look how broadened that peak is. The giants really are giants. I mean, imagine just using such simple math and simple equipment, just looking at the colors of stars and being able to tell how fast they're rotating. So how do you get started? Well, let's finish up. First, a grading, as I mentioned earlier, almost any sort of camera, some sort of software. This is my software. RSpec stands for real-time spectroscopy because you can, in real time, you can look at a video and adjust your focus and exposure time in real time. I'm a rather old programmer. I've been programming since literally the 60s. So like some of you, I imagine, I'm just this old guy, but I'm one of the people who remembers punch cards and using them. And to me, even though static fits imaging, of course, is much more sensitive, but static imaging is sort of like old punch card days, right? You dump the cards in and then you have to wait for the result to come out. The cool thing about video is it's real time, it's live. It's like, you know, a full real live, I was gonna say timeshare, but even that's an archaic term now. So here's the software which I mentioned earlier I had tried. I'm good friends. I Zoomed with them this morning during another workshop for the AVSO. They're still very difficult to use, very powerful programs though. The last thing you might need would be a spacer or some thread adapters. And the reason for that is the distance between the grating and the sensor. You don't want it to be too big or too small because that changes how much the spectrum can spread out and you don't want it too dim or too compressed. But there's a little calculator on my site and you just enter all the specs of your setup here or you email them to me. There's a little form behind this link that I'll you know, you send me your telescope kit, you know, what the specs are and so forth. And I make a little screen video and show you what we're looking for are some green flags over here. It's pretty easy to do. It's a little bit of a speed bump as you get started. By the way, I use that term speaking to a club in the UK and they pointed out later that in the UK, they don't call them speed bumps. They call them sleeping policemen. I love that idiom. So there's wonderful books out there these days for this kind of thing. I want to talk a little bit about the Spectral Atlas. On my site, well, I've highlighted download, but I meant to highlight links. So I've been working on my show a little bit here, so I haven't proofed it quite as well as I needed to. This atlas here, this hat does get warm indoors. This book here is really fascinating. And just more than that, it's great. Here's a page from it, and you can see it's calling out all the different things you'd be seeing, how to identify it. Here's some oxygen, some helium. But listen, I'm a knuckle dragging programmer. I don't know the significance of any of these. Who cares if there's nitrogen there? It doesn't mean anything to me. So because I'm not knowledgeable enough. But the great thing about this book is there's all sorts of pros aimed at us amateurs. Oops. So much for that. Let's see if I can get back to the show. These books are aimed at amateurs like us who don't understand or don't have the background. It's not aimed at PhDs. So that in itself is a great book. One or two more slides here. Let's get my cursor set. We've got a great online forum. There's tons of people there who love to answer questions like I do. And of course, there's really quick responses because the group's so large. The software is free for 30 days. But here's the cool thing. Maybe you never plan to do this, but well, one thing at a time. Let me first mention that I gave a workshop, an hour-long workshop to about 100 people in the AVSO at an SAS conference down in LA, if you're familiar with it. And there was sample data. Everybody had their laptops, and we and they recorded the whole workshop, and it's available on YouTube. So you could download the software free for 30 days, download the sample data from the same page, and then follow along with the YouTube video. You could do that tomorrow morning. In fact, it's Saturday today. Some of us have trouble knowing what day of the week it is these days. So Sunday morning, you could do that for a few hours, even if you never planned to do this or didn't even have a telescope. Maybe you're an armchair, I was going to say armchair philosopher. I meant armchair astronomer. So, excuse me, when you were done that, you would have spectroscopy in your bones. So it's something you can do. So also the site has a lot of tutorial videos. They're 3 or 4 minutes long. It's me just walking through the software. It's not quite like drinking from a fire hose like tonight, but there's no big thick manual to learn. You'll be doing this literally in your first or second night out. You'll be capturing spectra. There are opportunities for pro-am collaboration. There's a lot of databases that amateurs can contribute to now. The AAVSO has one that's about a year old. The BAA in the UK has one. There's one in France for a particular type of star. Not as much opportunity as we'd like, but there's more coming, especially Stella Kafka, the great director, executive director of the AVSO, is moving the organization into this field, and her predecessor, Arnie, both being professionals, understand the importance of spectroscopy in the field. So we've come a long way in the last 200 or 300 years, as well as the last 50 or so minutes. I'd like again to thank you for inviting me tonight. Thank you, hopefully, for smiling or laughing at some of my jokes. For those of you who do outreach, public outreach, I really want to thank you, because I think it's the way we can pay it forward and pay it backward for the opportunities we've had and taken advantage of. I'm here to answer questions tonight, as well as by direct email or through the contact form on my site. Again, thank you all very much. And now we can try to answer some questions from the YouTube crowd.
All right. It was a wonderful talk, Tom. Thank you so much.
You sort of have to, grab your breath after a while. I know it's a lot.
No, I mean, no, it was fascinating. I'm so glad you have added that slide about contributions from women astronomers in field of spectroscopy, because that's something we don't get to see much. Yeah. And when you mention Annie Jump Cannon, my first thought went to, and the human computers, my first thought went to Hidden Figures. Mm-hmm. And how I learned about it through the movie for the first time. Yeah. And then also thank you for the new mnemonic, because yes, the way I learned it when I learned the spectral classes of stars was like, oh, be a fine girl, kiss me, or something like that. And like,
doesn't work.
and Marianne on the YouTube channel, like she just said that it was also going around as, oh, be a fine guy, kiss me. Like it's like one of those two. Yeah.
In the Me Too era, it just doesn't work anymore. We need to
exactly. Yeah, we need something which is gender neutral and like not.
This one isn't good. Just to remind people, okay, boomer, a fully green kilowatt matters. I'm having trouble remembering that already. But anyway, it's better than nothing.
No, I definitely like your version better. That's definitely much better. So I'm waiting for questions to come in the chat channel on YouTube. But like, meanwhile, one question I had was, and I think you kind of have answered this, but like when you were on that slide where you showed how to get started, yes, I was wondering if you have your own YouTube channel or like something of that sort where there are how-to videos available that people can go to learn more about, like how to actually set up the telescope.
Yeah, the equipment. I'm working on the telescope setup pieces, but it's pretty easy, and it's mainly on the videos on my site. I'm trying to remember how to share my
I
screen
see.
again. And that would be on the site under video are all the videos here. You can see there, for example, is that hands-on workshop I mentioned with a YouTube video and the sample data. But down here, also in the software, are all of these short videos that show you how to capture a spectrum. And there is a short getting started manual that comes with the software on the help menu that describes, the issues of, how to mount the grating, and the standard issues apply, but for any imaging, it's, exposure levels, tracking, focus. Other than that, it's surprisingly easy to do. There's nothing that's all that unique to capturing data with a grating, but it's a good question. And I actually, you and I before the meeting were talking about the astronomy I can do up here in Seattle, and it's pretty frustrating. If I had my phone on Zoom right now, I could show you in my living room. In fact, a quick story here. In my living room, I've got my C8 on the floor and the tripod. It's all ready to go out on the deck when we get a clear night, but it's been there now for a couple of weeks. And because we just don't get a lot of clear nights here. But the story is, I think some of the people here in the meeting may appreciate this. My wife, bless her heart, we were going to have a safe distanced cocktail hour with two friends on our deck. And so she said, you've got to put that telescope away, like in the closet. And I said, we're just walking through the living room. Why would it matter? And she said, no, you have to put it away. And I'm thinking, my nerd friends, like the attendees at this meeting, they'd see that there, and that would be a badge of honor for me. They'd be going, all right, guy, you've got your telescope good to go. You're ready. But the telescope went in the closet and then came out again after that evening. But anyway, any questions come up?
No, I think people are just complimenting your mnemonic a lot and like practicing that. It seems like. And I don't know if you have heard of this book. Gary recommended a book, a reference to the Harvard Women Computers, The Glass Universe by Dava Sobel.
Yes, that's a great
that came
book.
in as a suggestion. Yeah, I'm gonna put that in my list.
Yeah.
And
go ahead.
Speaking of books, one of the books that you showed earlier by I think Ben Harrison.
Yeah, Ken Harrison, that's correct.
Ken Harrison, sorry.
Yeah,
I just wanted to mention it for the benefit of our members or the audience here, is that we have that book available in our library, actually, in our astronomy club. It's a different issue that currently the library has to be closed because of COVID. But when you put up the titles, the front page of the book, it came. It
looked, it's a familiar book.
It looked very familiar, and like I was like, oh, we have this actually. And I remember it came as a donation, and like I was very happy to keep it around, even if like not a lot of people dive deep into this technology.
Ken's a great guy. He's been a big help to me over the years. It's a great book. I think,
well, it's written for amateurs. So
it's written for amateurs. I think what often happens, is especially the more technical of us, the early adopters who are really bright and really capable, they end up writing things or giving talks that are too detailed. I mean, I kept emphasizing, you don't have to be a PhD, you don't have to build stuff, because Ken's book has a lot of details, which are sort of interesting, but you don't need to get started. And so I'm always worried that people will read a book like that and go, well, that's a lot of work. I could figure it out.
Be a bit overwhelmed by that.
Yeah. So that's why there's a couple other books here that I've listed. And again, they're under links on my site. This title is bothersome to me, but it's a good book. I don't really like carrying around a book that its title is Astrophysics is Easy, but it's a good book, So
speaking of grating, because I just saw that in the title there, Rashid has a question.
Oh, good.
Will the grating always create a horizontal pattern, or does it need to be rotated to get the horizontal capture?
Wonderful, wonderful question. The grating has a little line on the perimeter. The grating does not always produce. Give me a second here, see if I can find a real grating.
Sure, yeah.
I have a confession here, and this is just a blue filter that I've been using. And why? Because I don't want to get fingerprints all over my grading.
No,
But
makes sense.
yeah, but the real grading, and I don't have a sample sitting here, they're all in the other room, is the real grading has a little line right here. And you just put that line so that it's right along the plane of the horizontal pixels of your camera, and you're good to go. Typically what you do, and the software will do that too. Let's see, I'm still sharing my screen, so let me show you that. And I've even rotated this by 1.8 degrees because I didn't screw the grading on right. You can see it's a little bit at an angle. So the software has a way to rotate. Again, you can rotate things all over the place if you want in order to get them horizontal. It's not a good idea to do that when you're getting real scientific because it can introduce artifacts. But that's a great question. Typically what you do is you do a little bit of trial and error. You put it on, you take an image, you go, oh, that's not quite right. You rotate it a little bit and you just keep doing it till you have the image horizontal. But first night out, who cares? Rotate and just don't deal with it. The other thing I wanted to mention is you'll continue with a static fits camera to use whatever camera control software that you're used to using. And then what you can do in the software here is you can check this box, which says monitor whatever folder you want. And every time a new image shows up, just load it automatically. So it's pseudo real-time. That way you can work with your imaging software, nebulosity, or whatever you're using. And then when the image appears, it will automatically pop in here and you can evaluate it because you're going to be focusing for the deepest dips here. And exposure levels are particularly important also. Other questions?
Yeah, there's one more question. What kind of data can you gather by pointing at planets in our solar system?
Really good question. Unfortunately, most of the planets are too large to look at with a grading just like this because they're an extended object like M57 that we looked at. But you can see the methane, as I mentioned, in Uranus and Neptune. And depending on how sensitive your system is, I've got a visual aid I'll show you here in a minute. You can look at some of the more distant planets also. When you have a slit spectrometer, then you can look at all the planets and do all sorts of interesting things. And the thing I wanted to show you here, if this were the rings of Saturn, and much like that star we saw rotating, this edge of the ring is coming towards you, so you get some blue shift, and this edge of the ring is moving away from you. And you can actually measure with an inexpensive slit spectrometer, the $2,000 version, not the $3,000 or $4,000 or $20,000 versions. You can measure the rotational speed of the rings of Saturn or even of the planet itself. So that's the kind of thing that you can do. But mostly you end up observing stars. Stars are really the most common objects we look at.
I see. I think that kind of answers the next question that's just came in, which is, what is the good kind of an object for a beginner to start with, like a star or a planet?
Yeah.
But I think the way you just described it now, I think kind of answers that questions that we typically look at stars.
Yeah, typically it's stars. And actually the stars that we want to look at usually, let me share my screen one more time, we want to start in the getting started manual, by the way, is right there. It's about 10, 12 pages long, and it describes this. Different stars have different absorption lines. And it turns out these type A stars like Vega have the deepest, clearest hydrogen lines. And so those, because of that perfect temperature, those are the stars we start with. But here's something I wanted to show you that's pretty cool, just to keep people entertained, because it's not only entertain you, this is just very cool. So let's turn off that fill there for a second. And then what I'm going to do is open up a reference library and ask the software to show me what a type A star's spectrum would look like from a professional. Let's look at the whole image there. Notice that it's got dips right where more or less right where my dips are. Look how they line up. It's, it's pretty amazing. That's a nice confirmation that I'm on the right track for such a quick calibration. But also notice the difference. Notice that it keeps going up, whereas my data starts dropping down. And that's because our cameras get much less sensitive in the blue and ultraviolet. And so there's a way to correct your camera or correct this data so that your data really shows this plank-like curve. But the key is to always start on a type A star, and that's emphasized, as I said, in the documentation. Because look at this, I'm going to go over to like a type F star. You don't really see, actually, that's a bad example. What about a G star? There we go. There aren't these really deep dips for hydrogen like we saw in the type A star. So the A star is best to start on because the dips are so deep that we're more likely, the absorption lines, if I use the technical term, are much easier to see as we're learning how to focus and understand our data. But here's something that's sort of cool. I can go through all the stars in that OB-affine G KM order. See, I can't remember that thing. So notice that all of the energy on these type O stars, most of the energy is outside the visual light range. But watch as I go through. This is going to go through one star at a time very quickly. You watch over here and I'll describe what you're seeing. You're going to see the peak from Wien's law migrate over to the right for the cooler stars. There's B stars, A stars, F stars. See the peak moving to the right, K stars, and finally M stars. So this shows you the Planck curve that vary because the star temperatures are varying. This is another way that we can approximately tell a star's temperature. So using that information, here's a video that I made a few years ago of Albireo A and B. And we're actually correcting the curve for our camera. So that is the Planck curve for Albireo B. Notice it's a really hot star. It's 13,000 degrees Kelvin. So most of the heat, most of the energy is in the blue end of the spectrum, the hotter end of the spectrum. Now I'll play this video, and in a moment you'll see that now I'm sampling the other star. Notice that the shape of that curve is changed completely. This Albireo A, it's a double, but it's a much cooler star. It's only 4,000 degrees Kelvin, so more of its energy is over here in the red. So by studying the shape, the general spectral energy distribution, we can also learn something about a star's temperature. Again, just one quick and fun thing that I thought would be fun to show you. Other questions?
I just realized I had muted myself. That tends to happen a lot.
Yeah.
No, I think that was the last question I had for the night.
Okay.
But thank you so much once again. This was a wonderful talk, and the YouTube link is going to be available to watch later for
Good.
anybody.
Yeah, I hope you'll email that to me too. I'd love to take a look.
Yeah, definitely. I think I have it in the last email I sent you, but I can definitely send it out again.
Good.
And like I said, wonderful subject and wonderful talk. And if you are ever in Bay Area once the pandemic is behind us, we would love to have you in for an in-person talk at that point.
Oh, I'd love to meet all of you. This is a club that has a wonderful reputation. And I'm glad to have had a chance to meet all of you virtually, or at least meet one of you, but speak to you. And I look forward to the opportunity to speak again. And again, when things open up, I'm here in Seattle. I'd love to grab coffee, anybody who comes through town. Thanks again, and have a great evening.
Yes, thank you so much. I'm just going to end the streaming now. All right.